And a couple quotes from that. Overall introduction, exercise and fitness is a seemingly simple science sport that's unexpectedly relevant to everyday life, which is, I think we can all admit, how people see exercise. It's like, wow, that's relevant. Another one, I didn't realize that there were so many little things that I could do to improve my lifestyle. So nice to see that the NEP department's getting some recognition. And that also just a reminder that next week there is elections going on, so please make a plan to vote. And then shortly after that, we have Coffee with Professor with Dr. Dillon. So please make sure that you RSVP to that, and I look forward to the concept.
Yeah. You can vote.
Oh, yeah, so you can vote Memorial Union.
Tomorrow's 10 to 1.
Is that something?
That's my treat for being done today. I get to go vote.
Saturday.
Yes. tomorrow's 10 to
Not a
1.
trick.
Not a trick. It's my treat. Yes. Yeah.
Well, welcome everyone. Happy Halloween. Thanks for being here on this beautiful day. I'm Dr. Catherine Peterson. I'm an associate professor. I'm also associate director for the Division of Food, Nutrition, and Exercise Science. And today it is an absolute joy for me to introduce today's speaker. In preparation for this introduction, of course, I was looking at Jennifer's CV, and for me, it was like a walk down memory lane because for as long as she's been here, I've been here roughly. She was actually the first, when I first got here, I was the director of the dietetics program as assistant professor. And her class was the first class that I was involved in the selection process. I'm not going to say when, but it was some time ago. And even back then, I recognized brightness. I loved her participation in my classes. She was smart. She had a quick, fierce wit, which I appreciate in people. And she had this ability to make connections where most people couldn't. And to me, that just screamed out scientist, right? So I approached her in your senior year and said, hey, do you think about working in my lab and continuing on in graduate program? And she pretty much said yes. I mean, I don't remember too much hesitation. And so she worked with me back then. I was doing a lot of animal work, especially in bone health and soy protein and soy isoflavone. And so Jennifer's project, we were actually looking at soy protein intake, soy isoflavone intake during lactation using an animal model. And do you remember that, Jennifer? We got a lot of press. We didn't really want this kind of press.
No, because we needed to get milk from a rat and meet the Fockers.
And I thought that was the greatest thing. So we got a lot of press out of that it started with, what's his name, Rose. He's now deceased, but he was a local, Rose. It was local, they named the music place after him over there, Eastern Mojos.
Rose Music Hall.
Yeah,
Yes, I
yeah.
remember.
Anyway, he was the journalist who picked up the story first and sent it out. So, you know, it caught a lot of attention. But anyway, in 2004, when she finished her master's degree with me, I wanted her to stay on, but she had other ideas, and I understood that. She wanted to practice being a dietitian. She wanted to go out and, you know, and practice what she learned. And so she did that for quite a few years. Being clinical dietitian, you were a director, manager of a food nutrition services, right? Then she went back into science and started doing so as a technician, senior research technician, working in the lab as a bench scientist, which I know you always love doing, and you're going to see that evidence of that today. And then you did some teaching for us in our department. I mean, it's sort of going all over the place. And then around 2009, you started doing more teaching for us. 2014, you actually full-time assistant teaching professor, moved up the ranks to associate professor in 2019.
2020.
2020.
The year, yeah.
2020. And then, yeah, the year. And then with our director of dietetics leaving, Jennifer stepped in the role, out and then back in.
Yeah.
In the meantime, she won multiple teaching awards. In 2021, just notable one, she won the Outstanding Dietetics Education Award through the Academy of Nutrition and Dietetics. This is a big national award, big deal. And then most recently in 2024, she was awarded with the American Association for University Women Dissertation Fellowship. And anyway, so she's done, so I could be here all day talking about Jennifer. I will say in 2017 is when
Yes.
Jennifer came to me and said, I think I want to start my PhD. And I was so happy. It took you longer than I was hoping, but we got here, right? And so she's been working on it steadily. She's one of the most tenacious people I've ever met, hardworking, tenacious, resilient people that I know. So it is a great joy for me to recognize you today, and please join me in welcoming her and supporting her in her talk today on vitamin D transport.
Very kind introduction, Dr. Peterson. Thank you. Darius, can they hear me okay? Okay. You all, I'm loud. I've had the I'm fortunate that I've had a lot of you as students, and so you know that I'm loud, or you're otherwise have known me in other ways. I'm going to press my timer because if you all know me, you know I can talk to a post. And so I'm keeping myself accountable up here. Today, I have some objectives for our next 35 with hand waving minutes, so I can leave time for questions. I have some that are pursuant to my research questions specifically, and some that are about the wider context of vitamin D. So specifically, you know, I like Bloom's taxonomy. If you didn't, I like Bloom's taxonomy. We'll spend some time making sure we're all speaking the same language, that when I say vitamin D, you know what I mean and what I'm talking about. And then particularly understanding what I'm talking about, why is it hard to find? Why is it hard to quantify? Why is it hard to pick up? And then within wider context, why does it matter? And how do we even get this vitamin D thing going? What I would then like to transition to is presenting literature. As you saw, the title of my talk had to do with HDL and its relationship with vitamin D. So I'd like to explore that, present some literature that is showing how HDL is involved, and then circle back around to discuss my part of my research question. An alternative absorption pathway when we choose to eat or have exogenous sources of vitamin D. So Dr. Peterson did a great job of introducing me. So very briefly though, I taught my first class when I was fresh out of my master's. My very first one was diet therapy. Some of you have taken that class. I've done all those things. I'm also a mom, and I did start my doctoral training one class at a time, like that Johnny Cash song, one piece at a time, right? And going slow and getting to utilize the benefits of being an employee. It's costing me more than a dime, I can tell you that, but it is certainly a benefit that I'm glad I have as a member of the faculty. And because I spent a lot of time doing this, and some of the folks that came today know me more in that role, it happens to be an amazing action shot by a talented photographer on an exceptionally hot day. And so, yes, there's a filter with that, but I'm also really sweaty, really sweaty. So if you didn't know, I've played roller derby since 2007. It is a philanthropic sport organization. And it's where I derive a lot of my resiliency, that community and that support. And we're always looking for skaters, always looking for officials. That's my last pitch. Let's talk about vitamin D, my molecule of interest. Let's get some baby pictures. How about it? So vitamin D, when I'm talking about it, I'm talking about cholecalciferol. So we can see cholecalciferol here presented specifically to look like its parent molecules, which is a steroid, or more specifically, a secosteroid. So the steroid are these fused four rings, but the secosteroid is this broken B ring right here. So I'm sure you can appreciate when we present ergocalciferol and cholecalciferol, the two major forms of vitamin D in the human, animal, fungi, plant world, that you can see how similar they do look. Now, I don't want to blow your mind within the first 10 minutes, but these are not the only two. There are so many vitamin D species out there, so many. You'll notice that they all vary. They all have this secosteroid structure, but they vary based on the R group that's up there at the top. But like I said, mostly we're talking about vitamin D2, ergocalciferol that we find in fungi, from mushrooms to yeast, all of those, and cholecalciferol, which is predominantly in animals. So when again, I showed you how they look so that you could see how similar they look to their parents. But really, when they're out in the world, they look much more like this, much more planar of a molecule. So that's ergocalciferol, and here's cholecalciferol. And you're welcome to come and play with my toys later, but it is a very planar sort of molecule, right? So like a cracker, not a noodle, right, if we think about it that way. So this is when I talk about vitamin D, I'm going to come back to this so many times that I really hope you leave here understanding when I say vitamin D, I mean these chemicals. That is an important part to my research question and to our discussion today. However, we got to talk about those hydroxy metabolites of vitamin D. So knitting together the information we just had. So we have our vitamin D, and D2 and D3 both use these same enzymes. So from henceforth, I'm really going to talk just about vitamin D, meaning cholecalciferol, but I could be talking about either one. So either of those need to be acted upon in the liver by these two enzyme systems to become 25-hydroxy-D. Calcifediol is fine, but I'm going to call it 25D today because it's a little easier off the tongue. So important here, anytime you go get your labs drawn and you talk about your vitamin D status, anytime, most of the time you're reading literature and they talk about vitamin D, they're talking about 25D. This is a pro-hormone version of our friend vitamin D, and this is where we primarily store our vitamin D, is in this form. This is how we transport it. It has a pretty long half-life. So we go and look at our blood. This is what's going to be out there available for us to look at. But this is a pro-hormone. I know most of you have had some sort of endocrinology, so this is not the business guy. This is beforehand. The business, the one that does the action, is 125D. Or this is calcitriol, if you insist on being formal. And this is, as you can see, it has both of these carbons hydroxylated. And that's really what makes it so active and what has it interacting and doing its functions, which we will get to. But just like any hormone, a hormone is designed to be present in low quantities for a short amount of time. So this also is intended to be mostly 25D, but we need to be able to get rid of this active hormone form quickly when we no longer need it, when we no longer need it to do its job as a hormone. So we have a similar enzyme system here, and it will, again, I've highlighted in blue the areas that this enzyme works on, but it turns this 125 and adds a hydroxyl group on a 24, and chemically that's uncomfortable for it, so it usually becomes calcitroic acid, which we can excrete alongside our bile salts whenever we need to remove things through the GI tract. So all of this, again, can't happen without vitamin D, without the actual vitamin. Not talking about the prohormone or the hormone, but the actual vitamin. So I'm harping so much on this because you can find a kit. You can buy it. It's about $600, a 96-fold plate, to do this. You can buy it. There is no kit to find my molecule of interest. None. Doesn't exist. So I have to go back, and what I want to switch a little to now, my objectives, you saw, talk about how do you find my molecule of interest? What do we do there? So some other important things to know about vitamin D is it's happy by itself. It doesn't really doesn't want to hang out with water at all. It'll sort of hang out with triglycerides and long stringy kinds of lipids, but it doesn't particularly like that either. So what I had to go back and do is look in the literature, what are our options for being able to separate lipids? So very briefly, because I have to set up what it takes, no kit, remember, no kit. So one of the most foundational methods to be able to separate lipids is the Bland-Dyer method. And it's where you take these three chemicals, so chloroform, methanol, and water. Chloroform hates water. Methanol, meh about water. Water, yay, water. So what you do here is you put these in there, you shake it up, or you centrifuge it, and that allows for the lipids that don't want to hang out with water a place to go and hang out together. They get separated, and then you have all of those polar water-loving compounds on top. And that lets you be able to get at your molecules that are more interested in being with other lipids. The problem with that is that all the lipids are down there, all of them. And I'm not always interested in all of them. Talia's like, yes, there's a ton of lipids that are down there. That doesn't help me find my cholecalciferol. So I would need to do some cleanup, to use a bit of jargon. So another method that's common is a solid phase extraction. So very briefly with this image, Whereas this black is actually in the real world a cylinder, so it's like cutting a cylinder in half. And where is gray is a packing material. And that could be different packing materials depending on what lipid you're interested in separating out. So you pour in different chemicals similar to your chloroform, methanol, and water to condition it, to get it ready to separate these lipids based on how much they do and don't want to be around water. So then you add your sample in there, you rinse this or wash this with different solutions, again, based on polarity, until you get to the last one that your molecule of interest wants to hang out with so much, it's willing to leave that too. You collect it or you elute it. So that's solid phase. So that's what I wound up having to do, was combine methods from roughly 1958 with a little bit of tweaking and 1985 to be able to find polycalciferol in biological tissue, so plasma. That's the other talk that I will give later in the spring. Okay, so very, very briefly, because I want you to have some appreciation for this. So this is my modified liquid-liquid extraction based on the blind Dyer. Now, if you didn't know, EH&S really doesn't like it when you use chloroform. They don't like that at all. And so I had to use different solutes. Spooky. For those on Zoom, there's a ghost. Okay. So specifically, what I had to do is I'm working with plasma here is I needed to be able to knock my polycalciferol off any proteins that might be hanging around and give it a place to go in this methanol. So that was this step, knock it off there, give it a place to go, and then add this potassium compound here to make any charged lipids want to hang out more with water and get away from my molecule of interest. And then add this acetonitrile to be able to draw it out and give it a place to go, give it a place to hang out, essentially. So that was step one with my modified Fly Dyer. And then count them, 1, 2 solid phase extractions to try to clean them up. So it took this particular column, and this one went with, as you can see, the order water to 70-30 methanol to just methanol, and that gets goes from polar to non-polar. Dry that down, concentrate it, put it in another, then again, add it again to this one, which went the other way. Started with water and then got less and less polar. And that allowed me to be able to have 0.5 ml of very concentrated lipid extraction, which should contain my vitamin D, but it also has my hydroxy metabolites. So what I didn't put on a picture is that there's another separation method that's high performance or high pressure liquid chromatography. It looks a lot like this, except instead of just letting gravity let it drip out, we pull our shit in with high pressure. And we use a different mobile phase to drive that. So I did that, and that allowed me to have vitamin D and its hydroxy metabolites. So yay, finally, right? Not just a kit that we go and buy. Yay, we have those, but now I've got to count it. So how do we count it? That gets into a different issue. So a lot of times how we count things has to do with its charge, or if we can put a little fluorescent tag on it and then shine a different light and make it light up. Vitamin D, again, just wants to hang out by itself. Really is not interested in hanging out with other types of lipids. So we have to be creative. It does not have any extra charges hanging around. So if we want to put it next to a magnet or give it some electricity, it doesn't care. And then it's kind of small, right? It's cholesterol. It's kind of small. It's not a noodly long, lots of carbons lipid. It's pretty small. So it breaks up if you were to like smack it with a hammer and see what were the pieces. Maybe I can put that back together. Enter a derivatizing agent. So this one, please, you can understand why I'm going to call it DMEQ, and I am not going to read its chemical name, but this is DMEQ, TAD, and look at all of these delicious charges that it has that would really make it easy for an ionizer to be able to separate this. So what this allows us to do, and I traced it because it was kind of hard to see. So imagine taking this and just like mirror image flopping it over right there. So you can see that this nitrogen ring likes to interact with this broken ring of the cyclosteroid. And sticking that in there gives it charges and gives it so much more mass. This is a bigger molecule. And what that allows with LCMS then is where these dashed lines are where it will break whenever we smash it. And so you can see right here, this peak of 247 corresponds to the DMEQ tag. This peak right here of 468 corresponds to this, whereas that last one, that range right here. So this allows us to be able to count how much cholecalciferol is available or is identifiable. Now, one thing to note here, I wouldn't expect you to have caught this because it's common. This has a hydroxyl group right here. This is 25D. We couldn't find anywhere in the literature that this documented will work for cholecalciferol. So that's what we spent quite a bit of time doing, was figuring out if this would work. It does. How much of this do we need to add? Is it different? Yes, it is. Cool. How much? So it took a while, but we got it. We have a nice method, a way to take biological substances in our food, because food is very different, and find cholecalciferol. So that was a lot, but you survived. Everyone's still looking really shiny. I'm very pleased about that. No one got lost there. I like it. So coming back to our objectives, we're speaking the same language on why cholecalciferol is important. Told you that it's not so simple to find it because it's a picky little molecule there. So I'd like to spend some time talking about the wider context. So you were very kind and sat with me through that. Why does it matter? I need care, right? Let's talk about that. So I need to revisit. We were talking about those hydroxy metabolites. Let me orient you to our picture. So you've seen something on here before, 125D, the active form. You've seen a cell. I know it doesn't really look like a cell yet, but it will. What we have not yet been introduced to is that five-sided picture there that says DBP, or D-binding protein. It has its own binding protein. It's an old guy that we didn't know what it did, so you'll still see it referred to in the literature as its group-specific protein of serum globulin, or GCP. It's an albumin family. It's a big protein, and it can carry lots of things, but this one really likes carrying vitamin D. And when it delivers to the cell, it can deliver by passive diffusion, so that 125 can hop off, and there's an intercellular D-binding protein as well. That's possible. However, you remember from your endocrinology or from 5 minutes ago that there's not a lot of 125 hanging around. Most of what's in your blood is 25D. You are correct. So what can happen there is, again, we can still have some passive diffusion coming. That's fine. But we can also have the whole complex brought inside the cell, and then the D-binding protein gets repurposed. It goes to the mitochondria to get that last hydroxylation, and then voila, we have 125. We have an active, ready to do work right there in the cell. There is, of course, because this is a hormone, local feedback loops there, and there's also a way to excrete to make sure if we don't need as much vitamin D, we can do that. So this is new to the story. So what does vitamin D do? Why do I care? Vitamin D, if it is involved in a slow process like cell differentiation, maturation, bone growth, has its own response element on DNA. So when it does go and bind, it has its own nuclear receptor, which we classically thought it was only a nuclear receptor. We know now that it's in the cytosol, it can hang on the membrane, more on that in a moment. But it can come in and dock, it'll heterodimerize with the vitamin A receptor and go and either sit directly in its response element, turning on and off genes, or we now know that it also interacts with histones and can have a lot of epigenetic effects, turning things up and down. So a recent report estimated 20,000 genes are affected by vitamin D. That's why it's important. It's a lot of what we do to be eukaryotic, to have cells that do different things, rely on these chemicals being able to help us manage that. But wait, there's more. We have learned, now we had this idea that vitamin D works quicker than that for some processes. We knew that when we looked at how calcium gets absorbed in the GI tract and vitamin D helps, but we didn't know how that worked. And then the pandemic happened. And we started seeing that people with better vitamin D status, better immune response, was all that about. So what we've learned is that there are vitamin D receptors on the plasma membrane, and they can participate in second messenger systems with phosphorylating different proteins inside the cell. And again, the classical of calcium entry from the gut and phosphorus metabolism in the kidney is all of these non-genomic effects of vitamin D. So that's important, but remember what we're here to talk about. None of this can happen optimally if you don't have cholecalciferol coming in, because we don't make intrinsically 25D or 125D. We have to get it some other way. So it's important to look for the precursor, how we actually get this vitamin D in. Well, how is that? I'm so glad you asked. So there are two possible ways that humans do this. So we'll talk about the one first, just because I like talking about it first. So humans can photosynthesize. We can make vitamin D from the sun. Very briefly, again, because I have a lot I wanted to talk with you about today, is we need a particular wavelength to be able to penetrate to the skin. This is the precursor. And we need this wavelength to take it from this precursor to break that ring open to become a cyclosteroid. We need heat to make sure it stays that way. And then, so this is what we can do. But there are barriers, a lot of them. So if you notice, the angle of the sun has to be picky. So that means that the time of day, because, right, we turn. And so the time of day matters. There's only making vitamin D in a particular time. The location you are on the earth, when the earth is pointed towards the sun, you have more opportunity. When it's pointed away, you have less. The other part is latitude. So if you're outside of the Tropics of Cancer, there are certain times of the year that you can make vitamin D and that you can't. Last season, which gets that seasonality as well. The other part, skin cancer is real, right? And so we don't want skin cancer. So we block the effects of UVB because the effects of all UV because it prevents skin cancer. And we know that. But we also know it prevents making vitamin D. And our natural UVB blocker of melanin also blocks the ability to make vitamin D. Lastly, not all skin is created equally with its ability to make vitamin D. So the skin on, I don't know, the underside of your chin has a different ability to make vitamin D than the skin of the back of your neck. They're different. So they won't be able to make enough. So if we are supposed to, because this molecule controls so many genes, if we're supposed to get it from the sun, we have all these barriers. What is one to do? Well, what's the thing that I hope that you do more than once a day? Eat. Eat, right? So let's look at that. What are food sources? Well, naturally occurring cholecalciferol, so many. That was my point, but let's orient and then do more. So this red line is the recommendation for adults 1 to 70 on how much vitamin D they should get in a day. So if we notice the top 3 that are going to be the most rich sources of vitamin D, those are the only ones that are naturally occurring that are worth a lot as far as like value in your diet. If we want mushrooms to have vitamin D, we have to zap them with UV. They make it very similar. They make ergocalciferol like we make cholecalciferol, same process. They don't wear sunscreen as much. And these are fortified. We put them there. We've chosen that these are vehicles that we are going to provide vitamin D in different populations. Otherwise, they're contributing, and there's other ifs, ands, and what have yous on how much these will also have in there. But the long and the short is, food is also got some problems and some barriers. Just talking about which foods. Shall we talk about how we absorb it? We shall. Let's do that. Okay, so coming up at the top, these are exogenous sources, right? Endogenous would be photosynthesis. So I do want to call attention to, it has 25D, that's calcidiol, and 125 up there. Those are prescriptions that one could have should they need to overcome a severe deficiency. So I wanted to include those in this diagram as well. So when we do eat it, again, vitamin D is pretty darn stable. The acid in the stomach doesn't really mind too much, but I did want to point out a thing, because it'll become important in a moment. foods and non-human animals will esterify vitamin D. Humans don't. So when we need to get vitamin D from food, especially those naturally occurring, they may be esterified. Human beings don't do that. So that's what happens in the stomach. If moving out of the stomach into the intestine, if you're taking those hydroxylated, they go in the portal system, probably hops right on D-binding protein and zoop, away it goes. As I say probably, you can see there's plenty of research questions here. But what you'll find in all of your textbooks, Dr. Parks knows because when I came to her with this question, she was like, nuh-uh. And then we had to go and look and she was, okay. So that was a paraphrase. So looking at this pathway, it makes sense that we would think that chylomicrons are the place to put dietary vitamin D. It's where all the other fat-soluble vitamins go, but they don't look anything alike at all. Vitamin E has long noodly arms. Vitamin A has two noodly arms with rings on either end. And vitamin K is weird anyway, but it's also noodlies with rings on it. So structurally, they don't look the same. Why would we think they go the same? We'll get there. That was my thinking as well. But they do the whole lipid digestion, so micelles and all of that. And they get inside the enterocyte using known cholesterol transporters. I took that out of here because it was only known after 2013. 2001-3, yes, 2013, where we found out that, oh, vitamin D actually uses cholesterol transporters. And we make medications that block these. And those people, so you can imagine, struggle a little with vitamin D. So since I brought up barriers, let's talk about it. The foods that we eat a mixed diet. You should please eat a mixed diet. Don't eat just one thing, okay? But other fats affect how much you absorb vitamin D as well. So longer chain fats, polyunsaturates, they can decrease. Monounsaturates tend to increase. Fiber, so the type of carbohydrate we don't digest or absorb, gets in the way really down here and being able to absorb your vitamin D because it gets in the way. Additionally, remember I talked about those meds. So these are general classes, and this figures in 2020, we have even more meds that have come out in the market since. But other medications that affect how we move fats around in our body and absorb it also affect vitamin D. And the same for absorption typically can go up with these, but that's less of a problem. It's usually that meds get in the way of absorption and drive it down. So remember. So I'm thinking like, oh my God, Bean, how are we going to fix this? What does it need to do? I don't even remember. When it gets in, where's the next place it needs to go? Well, let's review. So once it gets in our body, in order for vitamin D to become the transport type, it needs to go to the liver. That's the first step. While other organs can do this part, we used to think it was only the kidney. Only the liver does this first hydroxylation step. So we need a way to get from the gut to the liver. Okay. Well, those are lipoproteins. Let's talk about them. Remember, Gerol, right? This is the family tree. There's cholecalciferol. When we eat cholesterol, we usually have cholesterol esters. They don't look too much alike. They don't behave too much alike. So let's remember what our chylomicrons or what our lipoproteins look like as well. So generally, I'm sure you've seen a diagram much like this in your textbooks, what it looks like on the outside. An outside layer that doesn't mind water and an inside layer that really doesn't like water. This looks similar, right? That's cholesterol. Looks a lot like our vitamin D molecule. Mostly that associates with the outer part. Mostly it goes on the inside with those esters. Again, these are great questions, right? Wouldn't it be nice to know? But then other information, so just thinking structurally, we know roughly the chemical component, the lipid components of these lipoproteins. So for our chylomicron, which is again what your textbooks will tell you, they're vastly triglyceride. There's a lot of triglyceride in those. And as we get smaller and smaller, there's less triglyceride, more protein, and the light green is more of that free blue. I'm not colorblind. Is more of the free cholesterol. So looking at those, there may structurally, chemically be more likely carriers here. So this was my thinking. So I don't know what, 2017 to 2020-ish. This was my thinking. I kept thinking about it. I was like, this doesn't make sense. Structure, function, structure, function. What is going on here? So this is where I started thinking about HDL. Because let's look at it all the way down there at the end. Not a lot of triglyceride, a lot more free cholesterol. Maybe that's where it could be. So I went to the literature. Well, let's remember first, nobody's looking at cholecalciferol. That's been my problem a lot of times. People be like, oh yeah, vitamin D does blah, blah, blah. It's like, that's 25D. Sure, I'm talking about cholecalciferol. So please remember, the literature that's out there is going to talk about 25D. And I'll highlight that as much as I can. So particularly this study, all premenopausal women, so that's the whole group, and they were all provided 200 milligrams of fenofibrate. So this is a medication. This purpose is to decrease atherosclerotic risk by decreasing your bad cholesterols and increasing your good HDL. So that was the purpose. That's why they chose this. They wanted a way chemically to increase HDL. And then they divided their subjects that they recruited. Group A has vitamin D deficiency as measured by 25D. Then we have, and they're not on a supplement, they're not treated. Then we have group B, who is deficient but on a supplement, and that's a big dose, but that's what you can buy over the counter. It's not like ridiculous. And then group C, who is native sufficient. So they have adequate vitamin D status without having a supplement or anything like that. So they put these women on this medication for 6 months. Extra info, because I think you're going to ask about it. They were on a therapeutic lifestyle change diet. So that meant that it was low fat, higher fiber, calorie controlled. For my exercise folks, they had them exercise pretty stringently, 30 minutes a day. So trying to keep that the same for everyone. No, right? 30 minutes a day. So then what did they find before and after? So it's a lot. Let me highlight to what I'm most interested in talking about today. So remember, they gave fenofibrate to increase HDL. Did they do their job? Let's look. So we have at the beginning of the study their baseline and after 6 months. So D, you can see down here. So if it's A, it's different from B. If it's C, B, it's different from C. And if it's C, it's different from baseline. So that's what I want to look at first. All of these have C. So all of them, yes, increase their HDL. And if you can see, these two groups that had vitamin D also increased it more. Okay. Now what about that vitamin D? How did that fare? Well, at the beginning of the study, again, group A we knew was deficient. We knew that. And they're not being treated. So they didn't get any better. Okay, that's what was supposed to happen. But in group B, whenever they were provided sufficient or they were native sufficient, then we can see it improved a little more. Right? I made that face too. So my question, could it be when exogenous cholecalciferol is provided that HDL plays a role in this transport to the liver for hydroxylation? Is that what's going on? Don't know. So it made me say, what else? Well, what if it's the other way? Okay. What if we are wanting to, we'll take otherwise healthy people and we'll give them vitamin D, and then we'll see what happens with their cardiometabolic function, right? That's flip-flopped. We intervened with their cardiometabolic function or their outputs, and we saw what happened with vitamin D. Let's give them vitamin D and then see what happens. So for this one, they took otherwise healthy, and I did healthy because they're healthy like Americans. About a third of them are obese, about 20% have diabetes, but they have no other disease state. So what's important here, and something to know, is that they wanted to evaluate, again, improvements in cardio and this atherosclerotic risk. So there's a risk score that involves all of these outputs. So orient you a bit here. We have men and women in this study, and we have some of the parameters. They have some glucose sensitivity as well, not just straight up glucose, but we have at follow-up what was the amount, and then we have what was different, and then looking, is that statistically significant or different? So skimming through for everyone, remember, They were providing vitamin D. They were providing it. Did they do their job? Yes, they did. People's vitamin D went up. They did that. What else went up or what else changed? Oh, well, the overall cardiovascular risk, HDL, both went up. And all they did here, again, they did not train these people. All they did was give them vitamin D and their HDL went up, which if we look across there at what the driver is, sure looks like HDL is the driver in changing this risk score, because what else really changed? And it does seem like it changed more or was had a greater effect in men, but men have less HDL than women do. So they have more space to wiggle within that norm than women do. So, So then looking at, because I think it's a striking figure, the numbers are great. The numbers tell you truths. So they compared this atherosclerotic cardiovascular risk score, and they looked at this by change. So on the axis over here, you can see percent change in their score, and everybody did better. Everybody did better. But what I wanted to highlight with this, the bars that are in red are the people that with that supplementation achieved sufficiency of vitamin D. They did it, gold star, banana sticker. Your vitamin D is where it's supposed to be. The blue, not quite, but they still had a positive effect. So even not being sufficient in vitamin D, they still improved their atherosclerotic risk score. Makes me think more. Could providing adequate amounts of cholecalciferol, like bringing that in, does it create a need for transport? Does it create more HDL, and more HDL can do more HDL job? Great question. So I have one more study I want to talk about with you, and then I'll wrap up so I can take some questions. Because what we've seen so far is we've seen a medication to increase HDL, and that increased vitamin D. We've seen increasing vitamin D, and that increased HDL. So what about lifestyle factors? What could we do that's not medication that could increase HDL? Well, my exercise friends, I have some candy for you at the end, okay? So this study, they recruited sedentary postmenopausal women from Iran, and they're otherwise healthy, and they do look otherwise healthy in the baseline. They exercised these ladies. So they had an exercise intervention group which did on-site training for 12 weeks for an hour, 3 times a week. So they exercised them. They did a pretty good job of taking records of what their diet was like. And then after this 12 weeks, they said, okay, bye. And then 5 months later, they came back and drew some blood to see what was the effect of detraining. So we have on top our control group and our exercise group. They label it as vitamin D, but we know better. They also don't look at the units too hard. But down here, these individuals, again, these are untrained, their vitamin D stayed the same. It didn't change. The only thing these individuals did was exercise. They went to the gym, they were there, they were putting in work. But the only thing that happened, look at this. At the end of the 12 weeks, yes, it's up. 5 months detraining, still up. Still up. There's no vitamin D supplementation, nothing like that. This is still the effect. Now, again, pursuant to our previous question, you'd be like, but what do those numbers mean, Dean? Okay, you're right. They started off in a bad place when it comes to vitamin D. They started off as a thirsty system for vitamin D. But the people that exercise got up closer to sufficiency, if not a little above, and we just saw that other figure. That helps with overall outcomes. That helps keep people from having atherosclerotic cardiovascular events. That still works. So I don't know. Another question. Could the way that exercise increases HDL, could that be a bigger role than pharmaceuticals for helping with vitamin D status? They're great questions. Great questions. So here's my theory and my idea. Then I'll be happy to take questions. So here's my idea. When we eat cholecalciferol, we saw that whole pathway, so I skipped all of that. We know it uses these, yes, some of it's gonna go in the chylomicron, of course, it's the biggest raft. And I really think if you give a big dose, it's gonna go on the biggest raft. But we don't eat big doses all the time, we can't, there's not enough in food. And whenever we make it from the sun, we don't use this pathway. We have other pathways to get there. So I really think HDL, whether it's coming by and picking up polycalciferol, whether it's the one that's made right there and tested, don't know. But we also have that binding protein. That could also be going on here. That's another way that it could be picked up. So there are alternative absorption stories that are possible that may be supported through HDL increasing vitamin D status. So these are my research questions, and I'm leaving you on that because then you have to come to my dissertation defense. Whatever that will be. So I did leave enough time. I made my timing marks. I was worried about it. So I'm gonna make some thanks. My committee members, I say I a lot, but really it's we. I don't do any of this in a vacuum. So I have fantastic committee members, my colleagues. I'll embarrass them. Darius, I didn't put you up here and I feel bad about that. I should have. Make my life a lot easier when I need to like shut myself in my office. And then they're like, cool, the door's open. I'll come ask you questions. I'm fortunate to have a mentor through the Research Dietitian Practice Group, Dolores Guest at the University of New Mexico. She reads a lot of my stuff. And all of my work is funded from Dr. Jean Lutan, our former division director. I'm the last of the F21C because it's not there anymore. And I'm doing the work that grant was for. So without them, I couldn't do any of this. So thank you so much for your attention. Ask me questions. Want to ask you?
I want to know what, like, so we fortify some things. Do we need to fortify or? I know what you just said is we don't even know how it gets in.
Yeah.
But clearly, if you give it, there's more in the body. You showed that. Do we need to fortify it, and what, if we don't, what bad thing will happen?
So I'll have to make sure, oh, I was gonna put on my witch's hat, so I can put on a literal hat, not put on my social justice hat. If equity is important and food is the vehicle, if we want to equitably distribute this nutrient. So yes, we should fortify food. And if I can report a little on the model that Finland has used. So we chose milk products as our fortificant. We drank milk. With cow's milk 3 times a day. We did that. So it was a great vehicle. It was super easy to do as
And
well.
that was in
Especially
Finland.
in children.
That's here in the United States and in Finland. Finland still drinks milk. Finland still makes milk products and fortifies everything. Their butter is fortified. Their cheese is fortified. Here in the United States, it's voluntary now.
What's voluntary?
Fortifying milk.
Okay.
It used to be required if you wanted to sell your milk across state lines, you had to fortify it with vitamin D. That is no longer the case. It's voluntary, but the industry is like, no, we're doing this because people expect to get vitamin D from us and we want to keep being that provider. But we don't have to fortify yogurt. We don't have to fortify cheese, butter, none of the stuff that we use to make milk. Some producers choose to fortify because they want that. So like Activia as an example, no sponsorship, is that they want to be like, look at this product. We are so nutritious. We have all the vitamin D you need. So then a question comes like, well, is dairy still the right fortificant? Well, most of us eat grains more regularly. But let's remember, I can go back to the figure if you like. Grains are a carbohydrate and they come with fiber. Fiber is probably going to decrease how much we can absorb. So although every culture on planet Earth eats a grain, I don't know that that's necessarily the best vehicle. So yes, I think food should be fortified. Which food? I don't think we can have a pan-globe answer to that. We have good food chemistry for that. I think it should be cheese, but that's my own personal, right? No, you said it would be to do with that. Yes, but that's my take on that.
So are you able to fortify, great talk, by the way. Are you able to fortify like the non-dairy cheeses, like a lot of like the cashew cheeses and stuff
You
like
sure
that? I mean, it's nuts, legumes, so you should have a higher fat content. content to it, but
You sure can. And to answer that question, non-dairy milks will keep the industry happy and see milks, right? Fortified beverages. They are fortified as well, and they don't have to be, but they want to be, because they want to say, we're just like milk. We can provide those same nutrients for you. So yes, you can. The chemistry is not even that different. And I know our food chemists are on Zoom and they're like, hopefully doing yay. But yeah, we can, and we should. I mean,
Rachel, so do you think that vitamin D that you make for the skin and the one we absorb from the food that they can absorb to the same part?
No. So whenever we make it from the skin, whenever it turns into that polycalciferol, it doesn't want to hang out in the skin anymore. Remember I said it wants to hang out with itself? Debinding protein is going to be the biggest R vehicle protein to come by and pick it up. The binding affinity for debinding protein it has so many binding pockets, so many seats on that bus, and they all are comfy to that 25D. So when we make it from the sun, we're likely using debinding protein, which comes from the liver. So the liver is definitely our nexus here on that.
Why do you think fish has such like high levels of polycalciferol like this compared to like?
Get paid for that. So this was a huge, there's this tome of vitamin D knowledge. It's 2 volumes, 5,000 pages. There's an entire chapter of vitamin D in fish. Why? Right? But it turns out that vitamin D, bigger fish. So if you notice those fishes were the big fish. They're not photosynthesizing it. They're eating the plankton. They're eating the sea vegetation that is at the top that makes it. So that's likely why it's in there. What do they do with it? The same stuff that we do with it, but that's likely why. That was your question. Like, yes. Why is it in there? Yeah. Yeah, and they do, they store it in their liver, which is why you saw cod liver oil was like, yes. And it was like the old school, yes. We cured disease with this food, rickets. Like, we don't have rickets anymore because we understand where we can get a super mega dose.
And exercise has an high concerns when well-trained athletes are they
that has been the trend in the literature. Yes. Has there been anyone yet, to my knowledge, that does a nice systematic meta-analysis? No. That would be cool.
Does running outside help?
That's what they do. So one study did mathematically model that. No, it's not even the running outside. When you take that away, there's still an improvement. Yeah, so it's not even the photosynthesis, it's exercise. Is it the HDL? I don't know, maybe.
After someone stopped regularly exercising, something did.
Good question. Don't know. So in that study, it was obviously longer than 5 months. Yeah. It always comes back faster, right? Go and exercise as frequently as you can.
I'm interested if there's been any, have we studied heart patients and their vitamin D levels?
That's where a lot of this comes from, is in populations with super, with poor vitamin D status and high rates of cardiovascular disease, which is the Middle East. There's a lot of, and that's why you saw Saudi people, Iranian people, because their vitamin D status as a population is so low, some of the worst in the world, and their heart disease rates are so high. So we do see them looking at that here. Yeah. They're not nutritionists interested. They're looking to keep their people healthy and alive. Yeah. Do you have a question?
Her question. So yeah, I was just curious what percentage of the population in different areas have vitamin D deficiency?
Most of us. So sorry. That's the shortest answer. Oh yeah.
And across the United States.
Yeah.
On latitude, does that matter?
Nope.
We're just all bad.
We are. If you want to read, there's this fantastic paper that's looking at the globe. Because again, when COVID happened, we were like, oh, vitamin D seems important. And those of us that are vitamin D researchers are like, yeah, of course it is. So that really opened a lot of people's eyes. So there's a fantastic article that's looking at COVID death rates and infection rates compared to vitamin D levels. And one of the big things in there, if there's this biphasic, so high income countries and low income countries are bad at getting their vitamin D. Medium income, better. Where they are on the planet, if you're around the middle of the earth, is not any better because it's too stinking hot and you're not outside and you're covering up. And so there's that part, as well as the whole like different cultures. Most of us cover up when we go outside, don't we? If we don't cover up, we put on sunscreen because skin cancer is real, because we live long enough to get skin cancer now. And so we're not good. I'm sorry. We're not, it takes work. You have to put effort in if you really want to have adequate vitamin D status. And what I hope to show you and that you are starting to think about is like, you know, I could work out and that might help. If I can't go out and get activity, if I don't really like fish, if I don't want to take a supplement, I'm not going to say it's going to fix you. We saw that, right? It brings you up, but it doesn't fix it to sufficiency. But it's one more tool you can use. The chickens cost $0 to that.
Fish,
Yeah. No.
Those vision they change over the seasons and to start track does HDL also track? Does it also change over the seasons?
That's a great question. I don't think anyone's looked at that. But yes, it does. So there's seasonality, just in case. I brought a globe, right? So if my fist is the sun, the southern hemisphere is in summer, right? Because it's my fist is the sun, northern hemisphere is in summer. So yeah, you get that 45-degree angle, but we also have that going on all the time. Yeah.
Yeah, but we don't know HDL.
We don't.
There's a paper on lipids throughout the year. There is a reference, but I
Yeah.
don't know.
If they look at HDL specifically,
They get HDL, we don't teach it yet.
I don't know. I don't know.
Would being malnourished negate the benefits of high physical activity on vitamin D status? So I'm thinking more about countries, and you mentioned low income. I'm thinking about India, for example, where you have a lot of people who are low income, very, very poor,
And also vitamin D.
malnourished, but very physically active,
Mhm.
active because that's what their jobs are. They're out there in the field, they're moving around.
The epidemiological data that I've looked at says that it does not negate it. That physical activity does not negate it. That individuals are still at low vitamin D status. Yeah.
I'm wondering about skin color too.
Absolutely, because there's that block as well to be able to photosynthesize.
I have one question. So to piggyback on that, we know that skin color affects how we absorb light, or how we make. Do you know if there's differences in absorption, like when we eat it from food, how years ago, how we absorb it based on the skin color?
Based on skin color, race, I'm not familiar with that literature, but what we do know is adiposity has a big effect. We don't understand the effect, but we do know that people, so race, no, but other things about a body, adiposity tends to be a big one. And people have rapid weight loss, such as with like, I don't know Ozempic, I haven't looked at that, but definitely with Roux-en-Y gastric bypass surgery, there's this flood of vitamin D that goes out in their system and then it's gone. Like, and then it's gone. Yeah, because it's coming from adipose and we can't capture it for long enough because then we break it down. There were lots of questions. Dr. Angwan, then I see you.
I was just wondering, what are your thoughts on enriching eggs with D3 and D2? I know there's a group in Cornell.
Yeah. And so with eggs as a particular vehicle, chickens can photosynthesize. So if you have chickens that are running around in the yard, they can also make vitamin D and then they put it in the yolk. But it's also their feed that's faster, right? To give them a high vitamin D food, and then their yolks have more. Americans don't eat tons of eggs, so it has the same problem that dairy does, right? Yeah, I know. Eggs got a bad rap, and then we're like, oh, eggs are okay. Yeah. What was your question?
Yeah, I was just wondering if you could speak a little bit about the sort of self-production of vitamin D. I know in this specific example, it was 4,000 IU, which is pretty typical in over-the-counter vitamin D supplements, and where it's not a water soluble like DNC, where you can just pee out that excess. I'm curious about what's happening when you're consuming that really high dose of vitamin D to sort of mitigate the negative effects and how that affects that excellent pathway.
So first I'll speak to the possibility of toxicity is theoretically possible. And if you look in the literature in this, because after the Industrial Revolution, when everyone was inside working in factories and there wasn't a lot of rickets was a problem. So it was a huge push to fix rickets. And so they fortified everything. And then there were a few kids that had the ultimate bad outcome in London, somewhere in England, but I think London. And so they're like, oh my God, it's the vitamin D, take it out of everything. But what we now understand is those kids likely had a processing disorder and they couldn't rid themselves. What we know now is that we don't really get toxicity if we're taking those supplements because we're gonna poop it out. That's what we're gonna do. The exception is gonna be babies. So babies are recommended to have supplementation, and if you don't follow the directions, they can get toxic events, but they don't die. They're just sick for a little while, which is still not good. So as far as supplements, so toxicity, it's something to keep in your mind, but it's not the ever-present danger that we thought it was in the 60s and 70s. So when it comes to supplementation, though, that is an option. If you have the ability to purchase and take it regularly, that is an option. Not everybody has that option. And so as far as amount, it seems to be safe. The upper limit is 4,000 IU, and even that is set with lots of wiggle room. So you can still go up to, I mean, pharmaceutical, briefly, pharmaceutical doses of cholecalciferol, if you need to bring up your vitamin D status, are like 50,000 IU. So like it's 1,000, 1,200 micrograms. It's a lot. And you take it every week for like months, and then you titer off of that. So you'd have to be making other poor choices about substances you put in your body and like taking a whole bottle of them to have a really negative effect.
Or you were. To kind of compound on that, do you think in the future that 600 IU recommendation will increase?
Oh, I have that. Yes, I hope so. I hope so. Very briefly, is that the way that we set our recommendations in this country is a minimum. It's a minimum for one particular body process. We chose how much calcium needs to come in to make your bones happy. That's what we're going to get that vitamin D. But we know our immune system needs it. We know other body processes need it, and they need more vitamin D. Our friends across the Atlantic have a higher set point for their vitamin D. We don't over here because we're a little risk averse over here. So will it? Yes. When? It's government, baby. Who knows?
So,
That would be our last question.
Okay.
so you're talking a lot about, kind of globally, we're all about vision. Doesn't come as a surprise. A lot of us don't eat well. We spend a lot of our time indoors. What are we doing differently lifestyle wise compared to, say, a long time ago, humans were getting this vitamin D to being needed, that we can change in our lifestyle? And is there a specific time in history that caused this?
Have chickens. Have yard birds. She said have chickens. Some of it comes back to the fact that we live a long time now.
Yeah.
We live a long time. I mean, like an octogenarian, you know, and like 300 years ago, right? So that's part of it, because we are constantly bathed in radiation from the sun. And we were outside when we moved our professions inside. That's not good. That's not helping us. I don't know. I don't want to say anything disparaging about food, because we have an amazing food system. You guys have eaten bananas, and some of you have never been to Central America. That's an amazing food system. And so we have those tools, but I do think it has to do with, we just live longer. And so we have to think differently about how we care for our bodies than we would have had to 500 years ago. Yeah. Thank you all so much for coming.